Welcome you all. This is, I don't even count how many talks we have. It must be 19th. Today our speaker is Marco Antonelli from
CAEN. It's just one syllable, it's CAEN.
Yeah, okay, from France, from CAEN. So after he took his PhD from University of Milan, he worked as postdoctoral researcher in Nicolaus Copernicus Astronomical Center, Warsaw. So he has interested areas in very large scale, from theoretical physics to nuclear physics to fluid dynamics. So today he will give us a talk titled "Friction in Superfluids, the curious case of neutron stars." So we thank you, Marco, for accepting our offer to give the talk here. So it's your turn now. Thank you.
Thank you for the nice introduction. It's a pleasure to be here. So yeah, basically, as you can see, the title is a bit like a sort of paradox, because you probably know that superfluids are known for their ability to flow without friction and to sustain persistent currents. But still, we will see how a superfluid can develop some friction in it, which leads to dissipation, and this in turn impacts on the observed dynamics of neutron stars. So I will focus on the physics, not so much on the observations behind the physics. But yeah, there are many possible ways to approach this topic, and I just had to pick up one. Just a quick reminder of what a neutron star is. A neutron star is like a sort of gigantic nucleus, but differently from nuclei. They are not held together so much by the nuclear force, but rather by gravity. Like 10 kilometers in radius, super dense. They are so dense that nucleons are really packed close together, that they start to feel some attractive channels of the strong nuclear force. And this gives rise to the Cooper pair information, like in standard BCS theory that we use to describe superconductors, terrestrial superconductors. And then those, let's say, Cooper pairs can condensate and ultimately give rise to the phenomenon of superfluidity. So here you can see a very rough sketch of what we think is a neutron star from the theoretical point of view, like with its beautiful onion shell and all the different theoretical possibilities, because of course we don't really know what it's in the inside, especially the inner core, but we have a fairly good understanding based on theoretical nuclear models of what should be what should be the constituents in the outer layers of this onion. So we start with an outer crust that it's made of normal matter. Normal matter means non-superfluid. And then there is also solid and contains a lattice of exotic nuclei. But at a certain point, this lattice is so dense and nuclei are so exotic, so neutron-rich, that some of those neutrons start to leak out from the nuclei and to form a sort of Fermi-Dirac gas that surrounds those nuclei. So the structure here is very similar to the one of a metal. So you know that in a metal you have a lattice structure, a crystal structure with this sea of delocalized electrons, and in a neutron star it's the same. But apart from the localized electrons, we also have delocalized neutrons. There are superfluid and that can flow within this sort of metal. So instead of sustaining only electronic currents, we may also sustain neutron currents in this kind of material that we believe it's present in the inner crust of a neutron star. So there are some defining properties of a superfluid at the macroscopic level. For example, the presence of stable quantized vortices. that are topological defects in the form of vortex lines that can fill up the superfluid domain. The fact that the superfluid can sustain persistent currents that are not dissipated. And finally, superfluidity can also affect the heat capacity, and in general, all the transport properties of matter are modified by superfluidity. And this can have a huge impact on the observed dynamics of neutron stars. For example, those are some phenomena we can currently observe. For example, with X-ray telescopes, you can keep track of the neutron star, of the cooling of neutron stars. And of course, with gravitational wave interferometers, everything that is linked to oscillations or neutron star merger gravitational wave emission. And finally, with radio telescopes, but also with X-ray telescopes, we can keep track of pulsar rotation, because as you know, we see neutron stars, most of the time we see neutron stars in the phenomenon of pulsars. So every time the electromagnetic beam sweeps the telescope, we see a beep and we record it, and we can keep track of the period of a neutron star and record how it changes over time. But the point is that the period of a neutron star tends to increase because of this electromagnetic radiation, but this is not always the same. Sometimes we have little spin-ups that are observed thanks to those timing techniques. And this is the glitch phenomenon that you can see here. And the point is that superfluidity is crucial to interpret this phenomenon. Not only because we believe that superfluidity, since it affects all the transport properties of matter, could heavily influence also neutron star cooling, because superfluidity affects the neutrino emission, but also the heat capacity of matter. And you know that at a certain point, the main cause of neutron star cooling is via neutrino emission. And then, of course, superfluidity also affects the possibility of sustaining more and different modes of oscillation, such that the spectrum of oscillation modes is much more richer in superfluid objects. So also the emission of gravitational waves, the spectrum of the emitted gravitational waves from neutron star oscillations should be accordingly modified. And then finally, as I already mentioned, pulsar glitches are thought to be the direct manifestation of superfluidity in neutron stars. In fact, since pulsars are isolated objects, they can spin up only if there is an internal superfluid that rotates faster than the observed components, and that sporadically allows for angular momentum transfer to the observed component. So just have a quick look at what pulsar glitches look at the from the astronomical point of view. Here you see some examples. The two most famous pulsars are actually the Vela pulsar and the Crab pulsar. They display rather different behavior. Like the Vela pulsar has this kind of very steep increase with almost no recovery, while the Crab has this beautiful quasi-exponential recovery that is almost complete. So you see that the pulsar is actually spinning down. Then there is this sort of step that leads to an increase of the spin of the observed spin frequency of the star, which means that suddenly in the pulsar time series, you find that the star has a spun up on a very short time scale. And then, of course, there is the whole dynamics of post-glitch relaxation, if any. So this post-glitch relaxation is thought to be due to the internal coupling between the internal superfluid and the observable component, while the post-glitch relaxation, for example, let's have a look at the Crab one, is basically due to some friction force between the superfluid and the normal component. So we have to explain how friction can develop in the superfluid. the point is to understand how a superfluid rotates. And I told you that one of the defining properties of superfluidity is the fact that they can sustain persistent currents, which is good for pulsar glitches because it means that you can store some angular momentum for the glitch in those persistent currents, but then you also need friction for the post-glitch recovery. And this is related to the presence of quantized vortices. So the point is that when you rotate a normal liquid, if you are in a thermodynamic equilibrium situation, the liquid rotates as a rigid body in order to minimize the shear and dissipation due to shear. But this cannot happen in a rotating superfluid. And instead we nucleate a certain amount of quantized vortices. Quantized here means that if you take the circulation of the velocity field around a single vortex, you always obtain the same number. There is the quantum of circulation that is related to some fundamental properties of the superfluid. But the point is that you can sustain rigid rotation, but rather you mimic rigid rotation by creating a rather regular array of those topological defects of those quantized vortices. This has been proposed long ago by Feynman and Onsager in the 50s. And the point is, the number of vortices, since they are quantized and stable, they do not decay, completely fixes the macroscopic rotation rate of a superfluid. So the angular velocity of a superfluid is directly proportional to the number of vortices inside the superfluid sample. If you want to spin up, you have to add vortices to the sample, and if you want to spin down, you have to remove vortices from the sample. But since those vortices do not decay, the only way to spin down a superfluid is to reduce the density of those vortices, which means that those vortices should migrate outward, and some of them, the outermost ones, should annihilate on the boundary of the superfluid. So they should exit the superfluid domain. And this is exactly what we believe happens in the inner crust of a neutron star. So here you see the sketch. In the inner crust, you have this lattice of a neutron-rich exotic nuclei surrounded by a Fermi sea of superfluid neutrons, which contain those quantized vortices. And if those quantized vortices pin to the impurities and to the nuclear lattice, they are pinned, they can't move, which means that the superfluid should maintain its state of motion while the normal component spins down because of electromagnetic emission. And this creates persistent currents in the inner crust of a neutron star, persistent currents of superfluid neutrons, because the number of vortices is conserved during the spin down because of pinning. So there is an imbalance, a velocity lag between the neutron superfluid and the one of normal matter, so of the nuclear lattice. Which means that this is the way to store some angular momentum as a current of neutrons in the inner crust of a neutron star. And if we release this extra angular momentum stored in this current by unpinning the vortices and letting them flowing outwards, we can explain the glitch mechanism. So this is, of course, in a very close analogy with what is known to happen in type 2 superconductors. And this analogy actually influenced this point of view, this interpretation of pulsar glitches, because, of course, type 2 superconductors are much well studied than the inner crust of a neutron star. We can make experiments that were already known when this proposal of a pulsar glitch explanation was put forward. So this branch of physics heavily influenced the current view on pulsar glitches. So what happens in type 2 superconductors? if you have a superconductor alloy, a superconductor piece of material, and you apply superconductor here, it means that basically the electrons are superfluid. And if you apply a magnetic field orthogonally to this specimen of superconducting material, you will see that in this case, you will create some small solenoids in which the electron tend to orbit in close orbits, like actually in a solenoid, that carry a quantum of magnetic flux. So the analogy is between vorticity and magnetic field. Quantum vortices is a neutral, in a neutral superfluid, carry a quantum of vorticity if you want, their circulation is quantized, while here you carry a quantum of magnetic flux, very loosely speaking. So what do we see in a superconductor? Superconductor can sustain persistent currents up to a certain critical threshold. So here I plotted the typical characteristic voltage current curve of a type 2 superconductor. There is this green line here. You see that for a normal conductor, for every applied current, you need a certain voltage to sustain that current because you always have some resistance. But for a superconductor, type 2 superconductor, you have that you can sustain some non-zero current also in the absence of any voltage. And this is the persistent current dissipationless limit. Up to a certain threshold, because there is a critical current above which you have to start to apply the voltage if you want to maintain that current, which means that the sample has turned into a dissipative state. And this is related to the motion of those small quantized flux tubes. So those flux tubes can be pinned to the impurities in the metal, but if the current, and this is the dissipationless limit, they don't move, but if the current is strong enough that they unpin and they can flow, they can wobble and excite excitations in the medium, which leads to dissipation. And so when they move, actually the sample is dissipative. And so there is an effective resistance due to the fact that vortices are moving. This is exactly what happens in a neutron star. So the analogy is this one. Let's imagine, let's picture from a more abstract point of view, a quantized vortex in the inner crust as a sort of little ball on a very rough surface. The rough surface basically is the pinning landscape that is due to the lattice and all the impurities in the lattice. So if there is no persistent current, no background persistent current of neutrons, basically the spinning potential is nearly flat. But as the star spins down, you start to develop this persistent current of neutrons in the background. So it's like tilting this complex potential, and some of those vortices can start to creep out because of this tilt in the pinning potential. If you do that more and more and more, at the end you can free most of them, and this means that the star is finally spinning up, entering in the dissipation regime. And then while it spins up, it means that the two velocity of the superfluid, the neutron component, and of the normal component are re-equilibrating. So the normal component spins up and the superfluid spins down. And this leads to an untilt, gradual untilt of this spinning potential. So this is more or less the abstract picture that we have in mind. So the problem here is that we have 10 to the 18 vortices in a neutron star, and we can't simulate all of them. Of course, 10 to the 18 is not Avogadro number, but it's big enough to be impossible to simulate. So we have to rely on superfluid hydrodynamics. Usually when you do hydrodynamics, you have one scale of separation from the microscopic scale, the scale of the fluid element, and the microscopic scale where you have particles. And statistical averages over a fluid element can give you the transport coefficient and all the macroscopic quantities that then you use in a hydrodynamic setting. So here, when you have a superfluid, you have actually 2 degrees of separation. The analogy is like walking in a forest, let's put it in this term. So when you are close to the trees, you are at the microscopic scale. Here, the trees are the quantized vortices. Here, you need a really macroscopic treatment to describe how those vortices are made, which is their structure, which are the dissipative couplings with the excitation, thermal bath, and so on and so forth. While you have another degree of separation, there is the fluid element length scale. And here, if we want to obtain smooth hydrodynamics, we can take into account single vortices, but we have to take a fluid element that contains several vortices. So vortices are already at a mesoscopic scale. There is something in between microscopic and macroscopic. So there is also this degree of separation before you finally can formulate a purely macroscopic closed set of partial differential equations that describe the hydrodynamic behavior of matter with superfluid vortices. The idea of the superfluidity is that now, if you want to construct this hydrodynamic description, you need at least 2 fluids. In our case, we need the superfluid of neutrons that can flow independently from the normal component. This is the whole game. You need some velocity lag between those 2 components for the glitch to happen. And so the idea is to extend the usual Navier-Stokes hydrodynamics to a sort of multi-fluid hydrodynamics. Here is 2 fluid hydrodynamics. One for this field Vn, there is the velocity of neutrons, and one for this field Vp, there is the velocity of the normal component, there is a normal fluid. And those 2 equations contain many terms, but basically they are very similar on their left-hand side to the usual hydrodynamic Euler equation for a single fluid, apart from the fact that now you have 2. And those 2 Euler equations are coupled via this mutual friction force. This mutual friction contains hidden inside it the average over the behavior of quantized vortices at the mesoscopic scale, at the inter-vortex scale. So if we are able to perform simulations of a bunch of vortices at the mesoscopic scale, we may have the hope to extract the correct form of friction between those 2 fluids. And this friction, this mutual friction coupling, can then be used for hydrodynamic simulations of neutron stars. So I put here the formula. It's not really important that you fully understand the formula. Just notice that it's very similar to the Lorentz force for a charged particle in a magnetic field, but instead of having a magnetic field, here you have K, there is the direction of vorticity, and X dot is the average velocity of vortices in the fluid element, while VMP is the lag difference between the superfluid neutrons and the normal component. So if you're able to extract this average over the vortex velocity, over the vortex velocity in the fluid element, then you have a very clear and simple prescription that can be demonstrated mathematically to extract from vortex simulations this mysterious term, this friction term that can operate also in superfluid matter. So this dissipative force is actually quite important, I believe. Usually when one talks about dissipation in fluids, One talks about shear viscosity or bulk viscosity. Those are two important effects that are also there, also in neutron stars, of course. And there are for sure very important when you have to model neutron star oscillations and mergers. For example, bulk viscosity is thought to have a kind of measurable impact on the merger dynamics. However, vortex-mediated friction requires the star to be rather cold, so we can't find it in mergers where matter heats up to above the critical temperature for superfluidity, but for sure this vortex-mediated friction can correct our current estimates of the late-stage cooling, because this friction also generates heat inside the neutron star, and the cooling is directly coupled to the rotational dynamics in the neutron star. So you can deposit a lot of heat because of this motion of vortices. And this, of course, affects the stage cooling of mature neutron stars. The effect is not big, but it's also operating for a very, very long time. So the cumulative effect in the end can have some, can lead to some sensible correction to the cooling curve. For neutron star oscillations, the same. If the oscillating neutron star is superfluid, this vortex-mediated mutual friction could damp the oscillations. And then, of course, it's also relevant for pulsar rotation because of everything I just told you. So let's try to quickly have a look on how to perform this kind of vortex simulations to extract the mutual friction. So 1 year ago, we developed this kind of kinetic approach where we keep track of the position and velocity of an ensemble of vortices, like 1 million, and you simulate their motion in a fluid element. So each vortex is immersed in this sort of rough surface, and we constantly tilt the surface to keep track of the average velocity of the vortex ensemble as a function of the tilt angle. The tilt angle is directly related to the background velocity lag between superfluid neutrons and the normal component. And in this way, with this simple toy model, you can extract the curve of the mutual friction force as a function of the background velocity lag. And this is more or less what we found. So we modeled the velocity of each single vortex as this kind of force here that is called Magnus force, a friction force with the normal component that is directly proportional to the velocity of a vortex, plus a disordered pinning landscape force field. We solve the dynamics for those 1 million vortices, take the average over x dot, that is to obtain the average vortex velocity, insert it in this simple formula, and extract the mutual friction. The mutual friction has two components. The component 1, directed along the background neutron current, and component 2 that is orthogonal. So we're interested in component 1 because component 1 is the one along the velocity lag along the neutron superfluid current. So is the one that can act to dump this superfluid current, which leads to momentum transfer to the neutrons and the normal component. That is what we're interested in when we talk about glitches. So component 1 is this one, is the blue curve in the plot. And we found that actually the analogy with type 2 superconductor is completely accurate. Not surprisingly, because this toy model is very general and can be applied also to type 2 superconductors. So we found that up to a certain critical threshold of the background neutron velocity of this velocity lag, basically VMP, up to a certain critical threshold of VMP, the difference in velocity between neutrons and normal component, the mutual friction is zero. You have no friction, which means that the vortices stay pinned. And up this threshold, the current is so strong that pushes vortices away from their pinning positions, and vortices start to creep in the material. And so we asymptotically reach this linear regime that is the typical linear regime that you expect when you have no pinning. So this is the general picture that you have for mutual friction, and with those vortex simulations you can really extract quantitatively the form and intensity of this kind of vortex mediated friction. So this is just the quantitative results for this friction. I just want to point out a very interesting fact. If the random pinning landscape is actually, if the pinning landscape, sorry, is random, the transition is rather smooth. So like this case, where you see that the solid line has a smooth transition between the dissipationless limit and the dissipative limit. But if you are in a regular pinning landscape, the transition is really abrupt and discontinuous. So you have literally zero friction up to a certain critical value, and then in a very discontinuous fashion, you switch on dissipation. So maybe with hydrodynamic simulations in combinations with pulsar glitch observation, in a future we will be able to assess if the inner crust contains a random pinning potential or a regular one. But it is still science fiction to the present date. It's just a possibility. But it's nice to see the theoretical effect of disorder with those vortex simulations. And another interesting thing is the fact that those vortex simulations actually go beyond hydrodynamics, because hydrodynamics is described in terms of partial differential equations. And partial differential equations, I mean, you can reverse them in time and they are deterministic and everything, while the glitch phenomenon resembles the dynamics of earthquakes, no? So you have a period of quiescence that can be short or long, and then suddenly something happens, something catastrophic happens, and it's very difficult to obtain this kind of behavior just with hydrodynamics. But here we see hysteresis in our simulations. So when we vary the background velocity between the neutrons and the normal component, we see that, well, of course, the vortices don't immediately follow the background neutrons because they are pinned for low velocities. So you have this step here. We modulated the background velocity as a sinusoid, and you see that they are pinned and they unpin, and they start to follow the background velocity of the neutrons. Then when they repin, they don't do that exactly at the same threshold of unpinning, but it requires a smaller background velocity of neutrons for the repinning. So unpinning, repinning is actually more difficult than unpinning. Let's put it in this term. You unpin to a certain threshold that it's, say, I don't know, 2, but you repin when the background velocity lag comes back to 1. And this is very interesting. It means that the system has an history dependence, like magnets or many other macroscopic systems in nature. And this, of course, is interesting because it gives a natural interpretation to the glitch phenomenon. If this hysteresis is strong enough, you can build up a certain velocity lag, a certain amount of background velocity of persistent neutron current unpin, enter into the dissipative stage, but then you have to dissipate a lot before repinning, and the game continues. So it's a sort of almost cyclic process that gives rise to glitches. Cyclic, but not periodic, because we can have different unpinning thresholds in different regions of the star, of course. So now just a little bit of observations in the last 2, 3, 5 minutes. I don't know. I hope I'm not running out of time. So there has been a few years ago these wonderful observations of a large glitch in the Vela pulsar. And this was an amazing observation because people were able to observe the spin up of the Vela during a glitch in the act by measuring every single pulse from the radiation beam of the spinning neutron star. So this, of course, boosted a lot of interest in trying to model the spin-up phase with hydrodynamic models, for example. And so here you see the data. Those are the arrival time residuals for the ones of you that know what this means. Basically, it's the time of arrival of every single pulse at the telescope. And you see that they are basically dispersed around 0. So the timing model was fitting the data very well, but then they start to arrive earlier than the timing model forecast, which means that the star was starting to spin up faster than predicted. So the spin up phase of glitch. So we tried to fit this nice set of data with a very, very minimal model. That is the natural three-component extension of a previous model that was developed by Baim and collaborators in 1969. So here we don't do real hydrodynamics because we take 3 rigid components. So everything is in terms of their rigid rotation rate, but this is the simplest approximation you can do. So omega dot p is the rotation rate of the NOMA component, and 1 and 2 are loosely interpreted as the superfluid in the inner crust and the superfluid in the outer core of the star. And you can see that we modeled here the friction between the P component and the superfluid 1 and 2 in terms of a linear friction. So we are assuming that unpinning has already happened, and we are in that linear regime of mutual friction that I showed you before. So you can solve this simple system and obtain the solution for the observed spin up, for the rotation rate during the spin up. There is this delta omega p. This delta omega p happens to be just the sum of 2 exponentials, and according to the parameters that you insert here in those variables, you can have a normal spin up, let's say, like a sort of quasi-exponential spin up, or also an overshoot. So a case in which the star spins up higher than the asymptotic observed glitch size. And this is an interesting possibility, and is also the reason why we choose to use 3 components instead of just 2, because with just 2 components, you can hardly have the exponential spin up without overshoot. But maybe an overshoot is contained in the data. And this is also what we found, confirming also a previous analysis of Gregory Ashton and collaborators that perform a similar analysis. They also found the presence of this overshoot. And the extra step that we took with respect to this previous study is that with this physical model, we can also give the value of the parameters B1 and B2, the one appearing here in the friction. So B1 and B2, the 2 friction parameters of the superfluid in the linear regime. And we found them to be broadly consistent with theoretical estimates, but I mean, the posterior results of the Bayesian fit are quite broad, so you need more observations to pin down some actual value. And then, of course, you can also pin down with this physical model and Bayesian fit. Sorry, you can pin down the value of the relative of the ratio of the moments of inertia of the various components, which is something that is related to the structure of the neutron star. So to our understanding of how matter is stratified and how much moment of inertia you have in the layers of the neutron star. So all this information is important also to nuclear physicists, because in the end they want to compare their structure models obtained from microscopic calculations with observations of pulsar glitches possible. So those are just my conclusions and final considerations. Just want to stress out that in the end, neutron stars are a very rich playground for theoreticians, because we can try to understand several interesting questions about both microphysics and macrophysics. You remember the 3 steps of separation from microphysics to hydrodynamics with this mesoscopic fluid element in between. And of course, as always in astrophysics, in the end, the king is observation. So in order to extract really those friction parameters, we need better and more observations of spin-ups in glitches. I think I can stop here. Thank you.
Thanks a lot, Marco, for the talk. I'm sure there will be some question from audience. Mehmet Ali Alpar has a question, so yes, please.
I can't hear anything.
Ali Hocam, buyurun.
Yes,
Hello?
can you hear me now?
Yes, now I can hear you.
Yes.
Yeah.
It was great to have you here, at least by Zoom.
Ah, hello, Ali. It's
Yes,
you.
yes.
Sorry,
Hello,
I didn't
hello, yes.
recognize you from the voice immediately. Oh,
Yes,
hello.
yes.
Hope
Hello.
you're fine.
Yes, and thank you for this really very lucid, very nice talk.
Thanks.
I have a question. Now, these simulations you made by representing the background superfluid flow, the bias, tilting your pinning landscape, etc. In effect, these are zero temperature simulations, right?
Exactly.
Because you place your vortices at random positions, and Magnus force and the Bernoulli effect, etc., will uniquely determine the initial velocities, and then you can follow what happens.
Exactly.
Now, have you investigated if you put in a thermal root mean square addition to the initial velocities as dictated by the initial positions? I mean, this might be justified, for example, by the fact that there is tension in the vortex lines, and that will dictate extra forces on them, extra velocities, etc. It's rather complicated, but you can just represent the velocity fluctuations, initial velocity fluctuations, as a root mean square temperature. And then if you add that component, I suspect this would give you a way of sort of having a mesoscopic representation of the assumption of temperature for vortex creep.
Yes. Yes, you're completely right. Yeah.
And I wonder if you have thought about this, or you have started doing something along these lines?
Yes, I already have the simulations. I was in so many projects that I didn't have time to really finish them and to write the draft. But the idea is to go exactly in that direction. So Actually, this picture of the tilting potential is directly taken from your famous paper, Ali. So the
Yes,
one of
yes.
1984. And if you add this thermal component, in the end, you can check with simulations or prescription for thermal creep, actually. So preliminary simulations gave me the following result. So the effect of random impurities and the effect of temperature is almost the same. So if you if you randomize the pinning landscape, or if you randomize the motion of vortices because you are simulating thermal effects, in the end, the output for the mutual friction is almost the same. So instead of, let's imagine that we do the simulation with this thermal component for the regular pinning landscape. At zero temperature, we obtain this flat and then abrupt switch on of dissipation. If you add the thermal component, of course, you are at zero when the lag is zero, but then this curve is smoothed in a very similar fashion as the smooth curve here in the random pinning landscape.
Which is the green one?
Is the green one. Yeah, here green and red are just different realizations of the same simulations, just with different drag parameters. So, but let's just take, for example, the red one, okay? So in the red one here, you have this discontinuous behavior in the first derivative, but in the random pinning landscape, everything is continuous. And if I go in the discontinuous case of regular pinning landscape and I add the thermal component, I obtain something that is extremely close, of course, as a function of temperature, to the random pinning landscape picture. So when you increase temperature, you smooth more and more this discontinuity in the first derivative, and you obtain something that is more continuous. And then the idea that I had was to test and to try to see if I can have enough vortices to see if I can fit the mutual friction obtained from the vortex ensemble simulation with your creep prescription, with the theoretical creep prescription that you and Erbil use in order to see if the simulations are in fact consistent with the theoretical expectations.
Yeah.
So yeah, this can be done, definitely.
Okay, but the follow-up question is, now in the picture you showed, you have linear drag, so that means it would result in exponential
this
timing
one
behavior, right?
Yes.
Right. Now, I'm just wondering if in these kinds of simulations, at any given value of temperature, if you actually start seeing something that corresponds to what we label as nonlinear response in the macroscopic creep model. Can you get to that?
Well, I think that the nonlinear response is here, closer to the pinning and unpinning regime.
Right.
When the lag is very, very big, the lag, and so the Magnus force, is much bigger than the effect of pinning. And so the effect of pinning is just a small correction, and you basically are in the linear regime for very, very big lags. But for small lags, the pinning influences the mutual friction. And so you see here that actually in this regime of small lag, just between 0 and right above the unpinning threshold, you are in a very non-linear regime, very non-linear.
Okay, I mean, I have many more questions. I've been in this is a it's a great way to start in that direction, I think, and maybe we can discuss that later on if we can arrange a meeting with Erbil and you.
Yes,
and
yes.
Maybe Bryn Haskell to
Would
see
be
what
nice.
can be done. Because you see, there is just one more comment. In the context of the macroscopic creep model, there is a certain tilt, a certain equilibrium rate of flow that corresponds to the pulsar's actual spin down rate.
Yes, exactly.
Okay, and so whether you end up in a linear or non-linear regime is a bargain, is a trade-off between two things: the actual value of the temperature and the actual value of that that equilibrium steady state spin down rate. Yeah. So there's a transition which is well defined, and you can define it in simple terms from statistical physics. But I'm just wondering, in this case, kind of sort of dynamical simulation, whether you choose your temperature, which I understand will be either a velocity dispersion or a dispersion in the actual random positions with respect to the lattice where you put your vortices. Okay. So if you play with the value of the temperature corresponding to the critical temperature, where you would see a transition from linear to nonlinear response, you can calculate that temperature. And whether you could see that transition between different types of response in your simulations is what I'm wondering about.
Okay, that's an interesting thing.
So we could talk about that. I think that it might be something feasible for you to do, and it would be very interesting to see correspondence.
Yep, it's a possibility. At the moment, I was just updating those results that, as you said, at zero temperature to see how they vary with temperature. And the overall effect of temperature is to smooth out those curves, whatever the pinning landscape.
Sure.
So, but yeah, then once you have those curves, you can start speculating on them. Thanks. Thank you, Ali.
Okay, is there any other question?
This was a train of questions also with discussion.
Sorry. Okay.
No. It was very interesting. Thank you.
Does it mean you have a question or you liked it?
I have a question.
Okay, then.
Marco, thank you very much for the very nice talk. I have a quick question. Can the approach by Antonelli and Haskell 2020 be extended to the case for vortex line flux tube pinning in the core for the orientation of toroidal orientation and colloidal orientation of the flux tubes?
Ooh, that's a nasty question. Thanks. Well, okay, I'd like to say yes, but I don't like to say yes. Because in principle, yes, you can, but I mean, you can extend those simulations to account for what you're asking for. But the point is that those simulations are phenomenological in nature, and it's already quite difficult to set the value of those phenomenological parameters. I mean, the ones that you see here, plus all the parameters that define the pinning landscape. So here, the big problem is the following. You see that if we change the pinning landscape, the result changes by a lot. So the point is, which is the real pinning landscape we have to consider in those kinds of simulation for them to have something to do with reality. And the point is that we don't really know. And we don't really know for the inner crust, and maybe we don't even know for the toroidal magnetic region. But if there is a way to understand, at least more or less, how the pinning landscape should be settled, in the toroidal region, then the answer is yes. So my answer is yes. I just want to be very, very cautious because everything depends on the quality of the input that you really put inside the simulation. Otherwise, you may obtain just random random results that have nothing to do with the real physics of a neutron star. So yeah, but in principle, you can do that. The real difficulty is to understand how to model the pinning landscape when the actors are the vortices and the flux tubes in the toroidal region.
Thank you. I think toroidal arrangement of the flux tubes in a sense resembles the case of regular pinning landscape.
Yeah, I was thinking something about that as well. So if you assume something simple, this can for sure be done. And we have some estimates of the energetics of pinning between flux tubes and vortices. So yeah, you can try to set up a phenomenological model and then run the simulation.
For the vortex and flux tube pinning in the core, the angular velocity lag is larger than the crustal nuclei and vortex line pinning. So maybe I think your model can be extended to the case of vortex line flux tube pinning in the core.
Yeah. I really thought about that because this is a natural possibility of extension. And if you have some suggestion about how to recreate the pinning landscape, willing to have a chat with you. Why not? We can try to see what can be done.
Thank you, Marco.
You're welcome.
Okay, thanks, Adil. Too. Is there any other question? So it seems not. Marco, thank you again for a very nice talk.
Okay.